Welcome to the National Transportation Safety Board's video series, V2X, Preserving the Future of Connected Vehicle Technology. This series is a part of our Most Wanted List advocacy for the deployment of connected vehicle technology in all highway vehicles. The NTSB's advocacy for connected vehicle technology began with a 1995 recommendation to the Federal Communications Commission, FCC, to allocate a dedicated spectrum for transportation safety communications. 4 years later, in 1999, the FCC allocated 75 megahertz for that purpose. Then, in 2013, we recommended that the National Highway Traffic Safety Administration, NHTSA, develop performance standards for connected vehicle technology and required that technology to be installed in all new vehicles. And at the start of 2017, NHTSA advanced the rulemaking process to mandate this technology in all new passenger vehicles. The NTSB was supportive of the proposed mandate and were particularly encouraged by the agency's proposed timeline to begin deploying connected vehicle technology in new passenger vehicles by 2021. However, NHTSA's proposed mandate stalled. The FCC shrunk the dedicated spectrum by 60%. Instead of connected vehicle technology being implemented, we have regressed. In this series, we will explore how we got here and what should be done to reverse the course and move toward the nationwide deployment of the connected vehicle technology. In today's episode, we will examine the research and the maturity level of this technology, as well as the impact of the FCC decision to substantially reduce the spectrum. My first guest today is Debby Bezzina. Debby is the Managing Director at the Center for Connected and Automated Transportation at the University of Michigan Transportation Research Institute. She holds a Bachelor of Science in Electrical Engineering, an MBA, and a Program Management Professional Certification. Debby has over 30 years of experience in the automotive industry and has served as a program manager for 18 years. Debby, thank you for joining us today.
Thanks so much for this opportunity. I look forward to it.
Since this is our first episode, we kind of want to set the foundation for the topics that we'll discuss throughout this series. In general terms, could you describe what connected vehicle technology is, how it functions, and where the term V2X comes from?
Okay, I'd like to start with just a small clarification. And when I say connected vehicles, it doesn't mean vehicles connected to the internet. It means vehicles connected to other vehicles, my vehicle to your vehicle to another vehicle, and also to the infrastructure. There's several key terms that are commonly used in the connected world. One, V2V, or vehicle to vehicle. The second is V2I, or vehicle to infrastructure, but also includes the reverse, infrastructure to vehicle. And third, V2X, so vehicle to everything else, pedestrians, bicyclists, you name it. Connected vehicle technology is really just a communications protocol that allows the vehicles, the infrastructure, and everything else to talk to each other on a secure, dedicated channel. But in order for everyone to talk to each other, they need to talk the same language. So a set of industry standards was developed to do just that. The standards define the language, and the language is really a set of messages that are transmitted and received by connected devices, either what we call an onboard unit, which means onboard the vehicle, or a roadside unit, which is installed in the infrastructure. Vehicles transmit a basic safety message every 10 milliseconds. So here I am, here I am, here I am. And this basic safety message contains many data elements, but on a high level, it has the vehicle speed, the GPS location, the heading, the predicted path, or what we think that the vehicle is going to go to, and some other attributes, like whether or not the driver is slamming on their brakes, which is referred to hard braking or panic braking. The infrastructure transmits different messages to interact with vehicles. The first is a traveler information message. This can be used to send out information about things like an upcoming curve to prevent run-off road accidents. So if a driver is going too fast for an upcoming curve, it would be getting messages about where the curve starts, the recommended speed, and then the onboard unit could warn the driver that they're going too fast. The traveler information message can also be used to transmit information about things like the pavement, such as the presence of ice. These are just a couple examples of the traveler information message, and it can be used for just about anything that you can think of. The next two messages are typically used together. The first is map and the second is FAT. So the map message is a geometric description of an intersection or other stretch of roads. In other words, it's a map. It's not an acronym. The signal phase and timing, or SPAT message, is broadcast from the roadside units and sends the signal state, so green, yellow, red, for each phase, which is the lane, and the timing, how much time is left of the signal state. So how long will the light remain green? The timing for each lane could be different. So for a left turn lane, it's different as the through lane, different as a right turn lane. And there's other important messages that can be transmitted. One such message is the personal safety message. The personal safety message is used to indicate the location of pedestrians or other vulnerable road users in intersections or crosswalks. And other messages are evolving. For example, a data sharing message is in development for automated vehicles. Vehicle sensors have limits. At an intersection, one vehicle may detect a pedestrian, but it may be out of the other AV sensor's field of view. Taking it one step further, a smart intersection could detect upcoming objects and potential collisions before they occur and share the information to vehicles in the area. A smart intersection has connected vehicle technology, but is augmented with sensors such as vision and thermal cameras and radar. This type of information can be shared between AVs for better and safer performance. It's my personal belief, and that of my colleagues, that smart intersections will be a game changer for a national deployment of automated vehicles. And I think that's really the gist of connected vehicle technology, but we can go down much deeper.
Okay. There's a lot there. Thank you for that. So if we had an instrumented intersection, one with equipped with various sensors and cameras, would they be able to detect vehicles, pedestrians, and other roadway users, regardless of whether they are connected? And that intersection would communicate to other connected vehicles out there about potential conflicts, such as a pedestrian distracted by their phone walking across the crosswalk on a red light.
Correct. And what we are doing, and what we'll do in Ann Arbor, and they've done this in Tampa as well, is the smart intersection can transmit information which they call a proxy BSM. So it essentially gives you that day one benefit. So now suddenly all the vehicles are transmitting information, even though it's just really sent by the infrastructure. And so if you have a connected vehicle, you're getting the information about all the vehicles in an intersection. So it makes that intersection much safer.
Interesting. Thank you. As you know, in May of this year, the FCC finalized the ruling that shrunk the available spectrum from 75 megahertz to 30 megahertz. Can you discuss the various V2X issues and the research that University of Michigan Transportation Research Institute has done? And can you also address with this how those topics are affected by the FCC's decision to shrink the spectrum by 60%?
Yeah, so that's a big question. And I think that going on, I'll end up addressing it in chunks. But one of the biggest chunks is that currently, in Ann Arbor, we use all 7 channels. And now they're telling us we can only use 1. So the FCC ruling is doing 3 things. So the first thing that it does is it reduces the channels, reduces the spectrum to 2 channels, one 10 megahertz channel for DSRC and one 20 megahertz channel for C-V2X. The second thing that it does is you're only allowed to broadcast DSRC on that channel 180 beginning in 1 year. So you have to migrate within the next year to channel 180, and it's not as simple as a software change. And then third, you won't be allowed to broadcast DSRC at all in 2 years. So basically, the FCC is choosing C-V2X as the technology to be used for connected vehicles.
Thank you. When we here at the NTSB talk about connected vehicle technology, or V2X in this case, we typically think about the imminent crash prevention application, such as intersection movement assist or ISA. But V2X application is much broader. Can you briefly discuss the other uses of this technology?
Yes. So connected vehicle technology addresses many problems, but it mostly is focused on safety, mobility, sustainability. So NHTSA estimates that connected vehicle technology could prevent 615,000 motor vehicle crashes a year, and that's a lot. NHTSA also estimates that connected vehicle technology could prevent 80% of all fatalities. Last year, there were 38,680 people killed on U.S. roads. So while less people drove during the pandemic, fatalities increased. Without the traffic, it appears that people are driving faster, making the crashes more deadly, crashes that could have been prevented. We have to remember that today's sensors cannot reliably detect and interpret what's happening on the road far ahead or in bad weather. We need connected vehicle technology to do that. Back in 2015, near Ann Arbor, we had a really bad snowstorm, which we get in Michigan. It was 16 degrees Fahrenheit outside, 0 degrees with the wind chill. It was blustery, it was snowy, visibility was low. One vehicle hit another, then another, then another. 193 vehicles in total were involved. 21 people were hospitalized, only one died. Local authorities used any bus they could get their hands on to go to the crash site to rescue these stranded travelers, all the while stopping their bus local service. The freeway was shut down for 2 days. Today's sensors cannot help in these situations, but connected vehicle technology can. And that's why it's so important to get connected vehicle technology on the road. But from the other aspects, for instance, mobility, urban congestion costs $121 billion in a typical year and causes 5.5 billion hours of travel delay. And I think I add to that every year on my commute to work. But connected vehicle technology can help. So U of M researchers led by Dr. Henry Liu have been developing dynamic traffic control. The traffic signal controller uses information from the basic safety messages being broadcast to optimize throughput and decrease congestion. Today's dynamic traffic signal control systems rely upon fixed location infrastructure-based sensors, for example, loop detectors. So these are embedded in the pavement. However, installation and maintenance of these detector-based signal systems is costly, and they're prone to frequent detector errors and failures. With connected vehicle technology, vehicle trajectory data can be gathered and serve as a data source for signal optimization. Based on this type of optimization process, traffic signals can be adjusted dynamically in response to traffic demand variation. My favorite example of this is when I'm sitting at a red light, there's no traffic in the opposite direction, but there's a line of cars behind me and it keeps getting longer and longer and longer. And wouldn't you like to just say, get that light to turn green? Well, this technology can do that. I also like to say, oh, it's you, Debbie, and it automatically turns green. And then lastly, focusing on sustainability, which is directed towards the environment. In a typical year, 2.9 billion gallons of fuel are wasted and 56 billion pounds of additional carbon dioxide are generated. One good example of how connected vehicle technology can help is what we call a green wave application. The traffic signal controller via the RSU can advise the driver how fast they need to go to make all the lights down the corridor so that they don't need to speed up, they don't need to brake, they just maintain the same speed. So this improves fuel economy while reducing the carbon footprint. So something very simple. And it's just using the SPAT and MAP messages that are being transmitted. But generally speaking, there are literally thousands of applications that can be developed that will address safety, mobility, and/or sustainability.
Fantastic. That's great. You've really established a nice foundation for us here. Let's shift to your research at the University of Michigan Transportation Research Institute. And let's talk about what you've conducted in the research you've conducted into the connected vehicle technology for about, I guess, 2 decades now, I believe it is. Can you spend some time talking to us about this work and specifically discuss the real-world effectiveness of these systems, and can they prevent crashes and save lives?
I'll try to give a concise answer for those many years of work. But the initial connected vehicle deployment in Ann Arbor was originally launched in 2012 as part of the US DOT Connected Vehicle Safety Pilot Program. It was governed by the ITS JPO Joint Program Office within US DOT, and this project was known as, at the time, as the Safety Pilot Model Deployment. It included over 2,800 vehicles and 25 infrastructure locations being equipped with connected vehicle devices. UMTRI led a diverse team of industry, public agencies, and academia as the official test conductor for Safety Pilot Model Deployment. The in-vehicle onboard units served to evaluate emerging vehicle safety applications that implemented DSRC technology to exchange telemetry and other situational messages between vehicles. And these vehicles were operated on public streets in an area highly concentrated with CV-equipped vehicles. Really what that means is that we deployed the roadside units in Northeast Ann Arbor, and then we recruited people that either live, work, or otherwise spend a lot of time driving around in Northeast Ann Arbor. And that way the concentration of the vehicles that were deployed were in that area. So the roadside units serve to convey traffic signal timing, intersection geometry, so the map, speed limits, and other safety critical infrastructure information to the onboard units. And as with the vehicle application, Safety Pilot Model Deployment served to evaluate vehicle to infrastructure, V2I, connected vehicle applications. Collectively, the model deployment was originally designed to determine the effectiveness of DSRC technology at reducing crashes by evaluating V2V and V2I applications operationally in the real world. You have to remember that the project was out of NHTSA, so that's why the focus was safety. It was also used to gauge user acceptance of the technology and to generate data to support estimates of safety system effectiveness. The project included a mix of cars, trucks, and transit vehicles, and was the first test of this magnitude around the globe of connected vehicle technology in a real-world, multimodal operating environment. The number one goal for Safety Pilot Model Deployment really was to collect the data. So Volpe was the independent evaluator for the project, and Volpe's data analysis clearly demonstrated the safety benefits of DSRC as documented in the paper, Independent Evaluation of Light Vehicle Safety Applications based on vehicle-to-vehicle communications used in the 2012 through 2013 Safety Pilot Model Deployment. That's a long one, but it is publicly available. So you can just Google that and it'll pop right up. And furthermore, though, the Safety Pilot Model Deployment, it was impactful. So that data and that data analysis was really the support for NHTSA's agency decision regarding connected vehicle communications that led to the notice of proposed rulemaking, which would have made DSRC-based V2V technology standard on all new vehicles. The proposed rulemaking set out to introduce FMVSS number 150 for V2V communication capability for light vehicles and minimum performance requirements for V2V devices and messages. Additionally, the lessons learned from this project were incorporated into the industry standards, including RSU 4.1, SAE J2735, SAE J2945, and IEEE 1609 suite. This project also was the starting point for the Production Security Credential Management System that was developed by the Crash Avoidance Metrics Partnership. Everyone knows them as CAMP, and it was implemented by Green Hills, who is now part of ISS. A bit about the security system. So each message that's transmitted is digitally signed with a security certificate. A message sent without a security certificate or sent with an expired or invalid certificate is ignored by all the other vehicles and infrastructure. The total cost of safety pilot model deployment was $30 million, with the DSRC equipment and deployment elements accounting for roughly $16 million of the overall cost. And as the safety pilot model deployment wrapped up in 2015, UMTRI began to transition and expand the effort into the Ann Arbor Connected Vehicle Test Environment under a Federal Highway Administration, FHWA, cooperative agreement. So the main goal for AACVTE was to transition from this model deployment to an early operational production environment. Secondary goals included serving as a national reference architecture for connected vehicles and infrastructure, conducting focused research, supporting other related research activities, and transitioning from government-funded to a sustainable environment. Currently in Ann Arbor, we have 75 roadside units deployed and nearly 2,000 vehicles. 4 of the RSUs are located at mid-block crosswalks along Plymouth Road. At those crosswalks, the connected vehicle technology is augmented with a vision system, and that system detects pedestrians and sends that information to the roadside unit. The roadside unit then transmits a personal safety message. Any equipped vehicles in the vicinity would receive the PSM, assess the threat, and warn the driver accordingly. In addition to pedestrian detection, we also have deployed forward collision warning to prevent rear end crashes, emergency electronic brake light to warn drivers when someone ahead of them is panic braking. And note that the vehicle may be several cars ahead and not visible to the driver, one benefit of V2V over conventional sensors. Red light violation to prevent drivers from running a red light, intersection movement assist to warn drivers if it's not safe to enter an intersection, say when another vehicle is running a red light or making a sudden turn. Curve speed warning to prevent drivers from going too fast in a curve. And lastly, ice warning, where sensors embedded in the road infer the presence of ice and send that information from the RSU to vehicles in the vicinity. We're also kicking off a new project in Ann Arbor, the Smart Intersection Project, SIP, funded through ATC-MTD program of the FAST Act. SIP will update 21 intersections with C-V2X technology and add smart sensors to pave the way for CAVs, connected and automated vehicles. These sensors, coupled with the connected technology, have 2 important functions. 1, detect vulnerable road users and share that information with others. And 2, detect unequipped vehicles and generate the proxy BSMs that we discussed earlier. So this effectively creates an environment where information about all vehicles is available, the equivalent of a 100% penetration of connected vehicles. Again, providing those with connected vehicles day one benefit. Collectively, these projects represent a $50 million investment in Ann Arbor. However, the Smart Intersections project will only upgrade 21 intersections and 200 vehicles to C-V2X technology, leaving the other 54 sites and 2,000 vehicles obsolete because of the recent FCC report and order, where we will no longer be able to broadcast DRC beginning in 2023.
You discussed the research UMTRI conducted since 2012, including the readiness of the technology, which can save lives today. And the longer we wait to implement the technology, the greater the cost will be. But are there limitations? Specifically, what kind of conditions may compromise the integrity of V2X communication?
You know, the only thing I can think of that would prevent it is if there's interference in the band. So for instance, with the FCC rebanding of the safety spectrum, they didn't really leave any buffer between us and the unlicensed band. And so there is a good chance that there's going to be some bleed over leading to interference. And then that would interfere with any communications.
Understandable. Many crashes that we investigate here at the NTSB involve vehicles traveling at highway speeds during limited visibility conditions, coming around a curve, or one that I'm very interested in, encountering a stopped traffic queue. Such crashes are frequently fatal. How does V2V technology handle such conditions?
So the answer is really the same for all of those, is because V2V is vehicle to vehicle, it's not limited by line of sight. So it can see around a blind curve where a radar sensor cannot. And I think that's really the basic difference.
Great. Where does the V2X technology fit in comparison to automated vehicles? Does V2X technology complement the limitations of vehicle automation? And can you discuss the shared perception and how automated vehicles would benefit?
In my circle and with my colleagues, we all believe that it's going to be connected and automated vehicles and not just an autonomous vehicle. And the reason being is that there are sensor limitation with AVs. And then typically all you can do with an AV is these low speed kind of transit applications. It's going to be harder to do the freeway speeds with just an autonomous vehicle. We really see that connected part is critical to an autonomous or an automated vehicle national deployment. So we're looking at CAVs versus strictly AVs. And when we talk about shared perceptions, I touched upon this a little bit with the smart intersection, is that you can share all these data amongst the vehicles with the infrastructure and back and forth, and so that you can get a better picture of your environment and be able to ascertain and decipher what's going on so that it can be safer, increase the performance of AVs, and just make the environment much safer for their deployment.
Great. Given that the FCC's shrinking of the spectrum has, I guess, already happened, is there sufficient room within the 30 megahertz for the shared perception application?
No. There's not even enough room for just DSRC, which is, they're making that go away anyways. But typically in the field, most people will see that first band, or the 20 megahertz band for CV2X, can be used for all these applications that we've developed today. So these safety applications that we use that are time critical. They see mobility and sustainability applications maybe as using your regular cellular network so that they're not as time critical. But when you start getting into the data sharing between vehicles, you definitely need more bandwidth. And they're looking at a minimum of 2 additional 20 megahertz channels, and we're going to have to find that somewhere else in a spectrum.
Understand. How does V2X technology help vulnerable road users such as pedestrians and bicyclists? Does it require them to be connected like wearing a device or maybe a cell phone, or do they primarily benefit through a detection by a connected intersection?
So in Ann Arbor, we deployed we actually deployed 2 systems. So I described the vision system, but the second system was a cell phone. So we gave pedestrians that crossed Plymouth Road frequently a cell phone so that we could kind of identify them for the research. But that connected up to the RSU and gave them pretty much the same information that you would see with the vision system. So the phone GPS would provide the location of that pedestrian as they're crossing the street, and then the personal safety message could be transmitted. But the short answer is you don't necessarily have to have the device. You can use the vision systems and they work well, but you can use either one.
Excellent, thanks. Considering the FCC proposed regulation published just this May of this year to allocate the remaining 30 megahertz spectrum for the use of only cellular-based LTE V2X devices and ceasing the use of direct short-range communication or DSRC, I have a few questions regarding the impact of that proposed regulation. First, can you briefly describe the difference between the DSRC and cellular-based technology, specifically LTE and 5G V2X?
Sure. So DSRC is like Wi-Fi, except that instead of using a wireless local area network through access points like we do with our computer, it requires direct broadcast wireless communication. So DSRC is defined by IEEE 1609 suite and 802.11.p standards. Cellular V2X or CV2X is similar because it also requires direct device-to-device communications. However, it uses the cellular PC5 link. So it is defined by the 3G, I always screw this up, the 3GPP releases. So release 14, which was in 2017, initially defined the CV2X services. Enhancements were introduced in release 15, but releases 14 and 15 are LTE based. So the 5G new radio, which is usually just called NR, it was defined in release 15, but that was for the phone application. So the 5G NR based CV2X is defined in release 16, and it continues to evolve the technology in release 17, which is currently ongoing. My personal readiness assessment for each is this. DSRC is commercially ready. There are many suppliers with mature products. CV2X is not quite as mature. There are a few CV2X infrastructure deployments, but CV2X vehicle deployments are very, very small, unlike what we have with DSRC vehicle and infrastructure deployments. The CV2X NR is not yet commercially available. Only a few engineering examples exist. CV2X is basically where DSRC was 10 years ago in the safety pilot model deployment era. Industry experts, however, think that we can take what we learned in the DSRC world and easily port that to CV2X, shaving years off the development cycle, but that remains to be seen.
Interesting. So let me ask you this, are these technologies interoperable then? Can like two vehicles, one equipped with DSRC and another with LTE or 5G, communicate with each other?
So both DSRC and CV2X follow the SAE J2735 message set, but they're not interoperable. Furthermore, the LTE CV2X and the 5G new radio, they're not interoperable either. So DSRC, only one message can talk at a time. In CV2X, each message is broadcast twice just to make sure it gets to its intended target, since more than one device can broadcast at the same time. The only way for DSRC and CV2X to talk to each other is through some sort of gateway. For instance, a roadside unit could, in theory, convert a DSRC message to a CV2X message, rebroadcast it, and that way a CV2X equipped vehicle could hear the converted message from the DSRC equipped vehicle. Another method is for each vehicle to have both DSRC and CV2X radios on board, which definitely is cost prohibitive in my opinion. To further complicate matters, the FCC report and order will eliminate DSRC altogether in less than 2 years. So a better question than is DSRC and CV2X compatible would be, who will pay for the conversion of the existing DSRC deployments that we have across the country? I'm trying to figure out how to pay for the conversion of the Ann Arbor connected environment, but that's only one deployment that we have in Michigan. MDOT has hundreds of roadside units. Macomb County has 200 roadside units with plans to deploy hundreds more. And there's at least one deployment in each state. So what about those?
Absolutely. That answered my next question in itself there. So let's shift questions to a little bit about performance standards in this case. Are there existing performance standards for DSRC and LTE V2X?
So there's many standards that define both DSRC and CV2X. The 1609 series is for DSRC, the 3GPP releases define CV2X. However, there are several standards that define the message set and performance that both DSRC and CV2X must meet. So in particular, the SAE J2735, the SAE J2945 set, and RSU 4.1, although developed for DSRC, need to be met by both. And all of these standards right now are currently being updated so that they're not DSRC centric, which they currently are. But typically, the CV2X manufacturers know that they need to send out the message set just like it's defined in J2735. It's only the communication that's different.
Great. So what does the cellular-based V2X have in common with LTE and 5G networks on our phones? And can these phones be used for V2X communication, specifically for imminent crash prevention applications?
Right now, no. So for imminent crash situations, you definitely want to use the PC5 link, which are not on a phone. There's also the matter of timing. The reason you're using it is direct communication is the latency. So for crash imminent scenarios, latency is everything. Normally when you talk about real estate, it's location, location, location. But with this, it's time, time, time. I need time. You need at least 750 milliseconds for a driver to react to a situation after they receive a warning. So you better make sure that you've got more than that in there. With just using the phone cellular network, you really don't have that guarantee about latency or robustness, but you do have that with the PC5 link. So you can use what they call the UU network. That's just your basic network that you have on your cell phone for applications such as, mobility or sustainability focused.
Great. I know I've asked you a lot of questions today, and I'm going to ask you one more. And in your own words and in your opinion, with your background, experience, and knowledge of this, how do we progress toward broad deployment of V2X?
So regulatory certainty is first and foremost. When the NPRM for DSRC was not enacted because of the new administration back in 2017, it gave rise to the introduction of CV2X. Now with the actions of the SEC, another delay has been added. It wouldn't be surprised if another technology is introduced that's touted as bigger and better, and then we all wait for that. In 2018, Dr. Jim Sayer, the director of UMTRI, wrote a white paper that calculated the impact of delaying deployment of DSRC and waiting 3 years for CV2X. First, I want to point out something very important, that it's been 3 years and still neither DSRC nor CV2X are deployed, a big part due to the uncertainty caused by the FCC. Dr. Sayer estimates that from 2019, when we could have started deploying DSRC and allowing for a 3-year rollout of new cars, in 5 years, up to 520,000 crashes and 3,152 fatalities could be avoided. Every year we wait, more accidents will occur, resulting in more fatalities and more life-altering injuries. Accidents that could have been avoided if we only deployed connected vehicle technology sooner. I always say that I have the best job in the world. I save lives. But in reality, I only lay the foundation for that to happen. I'm still waiting for all new cars to come equipped with the technology, something I believe will only happen with a clear national path stemming from regulatory certainty.
Debbie, thank you so much. I want to thank you for your time, and I appreciate you sharing all of this with us today.
It's been my pleasure. Thank you.
My second guest is Bob Kreeb. Bob joined the National Highway Traffic Safety Administration in 2010 in the Office of Vehicle Safety Research. He is now the Chief of the Electronic System Safety Research Division at NHTSA, where he researches the deployment and commercialization challenges associated with connected vehicle safety technologies. Prior to joining NHTSA, Bob worked for General Motors as a design engineer before moving to Booz Allen Hamilton, where he worked for both private and public sector transportation clients. He holds a degree in mechanical engineering and an MBA. Bob, welcome and thank you for joining us.
Thank you, Member Graham. I guess before we get into the details, I'd like to just thank NTSB for inviting us to speak about this report. We think the report was well done. It followed solid scientific principles, and we stand behind the results of the report. So thanks for the opportunity to talk about it.
Excellent. Great to have you here today. As you know, Bob, in May of this year, the FCC finalized the regulation that shrunk the safety spectrum dedicated to connected vehicle applications to only 30 megahertz. That regulation opened the other 45 megahertz to unlicensed Wi-Fi devices. Last year, NHTSA completed a study determining the impact of reducing the safety spectrum. I understand that the primary concern is that these unlicensed Wi-Fi devices, let's call them your local hotspots, would interfere with the operations of V2X operations. The FCC itself acknowledged this concern back in 2013. Why would these unlicensed devices cause interference, and can you talk about the results of this NHTSA study?
Sure. Thank you for the question. So first, maybe why would these unlicensed devices cause interference? So the radio frequency power levels from unlicensed devices, and let's just call them Wi-Fi devices, they do not abruptly or magically drop to zero at the edge of their allotted frequency. Rather, they spill over into the adjacent bands, and the transmission power levels gradually drop off the further away in frequency you move from their assigned bands. And so this phenomenon is called out-of-band emissions. And when Wi-Fi devices are operating in a band that is directly adjacent to the DSRC band, the out-of-band emissions from Wi-Fi devices will be present at the exact same time and at the exact same frequency as DSRC signals. And so the wireless message packets from both kinds of devices will collide, and that can cause them to either be corrupted or to just drop out. And essentially they interfere with each other. So they're trying to operate in the very same space at the very same time, and the physics just doesn't allow that. Perhaps a simple analogy is when there's a conversation between two people happening, and it's interfered with by a nearby third person who is talking very loudly. The communications just doesn't work exactly as intended. So that's the fundamental reason, is the out-of-band emissions and the fact that two different kinds of signals are trying to occupy the same space at the same time. So it just doesn't work.
Excellent. What impact would this interference have on the different V2X applications, specifically imminent crash prevention, that require very low latency and extremely high reliability of safety messages being delivered and received?
So the study itself, just to get into the details, examined the potential interference between unlicensed 802.11 AC devices, or again, let's call them Wi-Fi, and DSRC, with Wi-Fi operating in the lower 45 megahertz and DSRC operating in three different locations adjacent to Wi-Fi. So there were three different test setups. The first was with DSRC operating directly adjacent to Wi-Fi in a 10 megahertz band. The second setup was with DSRC operating with a 10 megahertz separation, or 10 megahertz away. And then a third configuration with DSRC operating at the very top of the safety band, and therefore with a 20 megahertz separation from Wi-Fi. And so for each of these configurations, the quality of communications between two DSRC-equipped test vehicles was measured, and these vehicles were positioned 75 meters apart. And then there was a number of different experiments done where those two test vehicles were positioned initially directly adjacent to the Wi-Fi transmitter, and then they were moved in 25-meter increments further away, all the way out to 500 meters. And so at each of these conditions, the interference was measured. And it was measured by something that we call packet error rate, which is a measure of the percentage of packets that were transmitted but not received. And just as a point of reference, packet error rates in excess of about 10% have been assessed by V2V safety system designers, the folks that are building these applications, as being excessive. And that's been determined through a variety of empirical testing and real world experimentation. And so, basically the experiment was at each of those conditions to measure the packet error rates at first with no Wi-Fi operating, and that was baseline. And then again, measure the packet error rates with Wi-Fi turned on. So again, we had 3 different locations for the DSRC signals, and then multiple locations away from the transmitter. And so what were the results? Well, first of all, with the Wi-Fi transmitter turned off, as you can imagine, the packet error rate was near 0 at all conditions. So even going out to 500 meters, when Wi-Fi was not present, the signal quality was near perfect. But when Wi-Fi was operated in the 10 megahertz band directly adjacent to Wi-Fi, the packet error rates were well in excess of 10%, even when the test vehicles were 500 meters. So even at 500 meters away from that Wi-Fi transmitter, we still got some interference. And in fact, packet error rate was, I want to make sure I got the numbers right here. In fact, packet error rate was measured at 50%, even at 350 meters out. And then we moved the DSRC signal to give us a 10 megahertz guard band or 10 megahertz separation. And when DSRC was operated at that point, the communications quality was still compromised with packet error rates in excess of 50%, as far out as 225 meters. And again, anything worse than 10% is bad. And then finally, when we moved DSRC as far away from Wi-Fi as we could, in other words, operated in that top 10 megahertz, with a 20 megahertz separation, the quality was still not great, with packet error rates, again, in excess of 50%, as far out as 150 meters. So, and there's a lot more details in the report. There's a couple of other different test conditions, and there's sort of continuous measurement. But those results, certainly suggest, a level of interference that could be an issue. When communications in this case, when communications quality is measured by packet error rate suffers, the safety applications that are relying on that V2V communications, they begin to have difficulty estimating the position, speed, and heading of the nearby vehicles. This is particularly important or particularly true when the vehicles are not able to be, quote, seen by other sensors like camera and radar, which I think, as you know, require a line of sight communications, and they can be impacted by different environmental conditions such as sun and rain and snow. And so the V2V communications are not impacted by those things. They don't require a line of sight, and they're not really impacted by environmental conditions. So in situations where the crash scenario is such that the V2V communications is important, the V2V application is going to have difficulty really having the kind of awareness of surrounding vehicles that it needs to, properly inform or supply the information that the crash applications need. And in those crash scenarios where V2V communications are important, the applications could be compromised and they simply wouldn't work as intended. And again, the caveat or the nuance I had referred to is this is in situations which are important for V2V to be working to begin with, which again are those situations that that occur with far too much frequency when there are challenging conditions, or when the other vehicle, so to speak, is not in line of sight. So that would be the impact of interference.
Understandable, very significant. Thank you for that. So based on your description of the study findings in this last question I just asked you, what would be the extent of V2X communication degradation in busy city locations that are likely to have multiple strong hotspots, as well as high volume of vehicles, pedestrians, and other roadway users?
Well, referring back to the study, this study was done in rather controlled conditions. The test vehicles were positioned 75 meters apart with no obstructions between them. And there were also no other surrounding vehicles. And so we did that on purpose to keep the results very interpretable, and clean. And so, directionally, the interference in the situations you suggested could be a problem, could be worse. But it's hard to speculate. I'm a little reluctant to speculate too much, just because unless you look at a specific condition, how the interference would play out is a challenge. We know under these conditions where there weren't other cars and there was a clean line of sight, we still experienced interference. And to try and answer your question as most directly as I can, at least directionally and theoretically, those conditions would make it even more challenging, and therefore interference could be, even more of an issue.
Thank you for that. What are some of the potential options for resolving the problem of interference? Well,
the most obvious option would be to be able to increase that separation. Some people call it a guard band, increase that separation between DSRC and Wi-Fi transmissions. As I mentioned earlier, the power levels begin to drop off the further away in frequency you move from the assigned band, and therefore, less likely to interfere. The other option is to tighten what they call the spectral mask of the interfering device. And it really means to limit the amount of spillover frequency that could be present in the adjacent band. And so tightening that spectral mask is one option for helping to reduce this problem. And we know that is possible with Wi-Fi devices. The out-of-band emissions limits can be tightened, and that's been demonstrated. Directionally, it would increase the cost of the devices to do that.
Bob, I'm not going to put you on the spot about NHTSA's future plans, but is there anything else you would like to add?
Yeah, thanks for the opportunity. Again, first, appreciate being able to talk with NTSB about our report. With regard to future plans, first, I would like to make it clear that this study was completed using dedicated short-range communications technology. And all the results are limited to that interference between that technology and Wi-Fi transmissions. As you know, with FCC's final rule, they are specifying a different technology be used for V2X communications, and that is cellular V2X. And so USDOT, it has a program being led by the Federal Highway Administration and the Joint Program Office within the Office of the Secretary to essentially repeat some of the work we've done here and to better understand how Wi-Fi might interfere with cellular V2X transmissions as well. And so that work's ongoing. And certainly as the results become available, we'll share them as appropriate. So thanks for the question.
Thank you, Bob. Thanks for joining us today, and I appreciate you sharing the NHTSA study with us.
Thank you. Really appreciate the opportunity.
V2X technology has matured, and the research that Debby Bezzina from Umtree discussed demonstrates that it is effective and ready to save lives today. Umtree also shared the predictive analysis showing that, had we begun rolling out V2X in 2019, we could have saved over 3,100 lives in the first 5 years and prevented even more serious injuries. The longer we wait, the greater the human cost of our inaction. We also heard from Bob Kreeb, presenting research from NHTSA, showing that the FCC's ruling to shrink the safety spectrum raises serious concerns regarding interference from unlicensed devices. This interference threatens the basic viability of V2X technology in the United States. So why have we failed to realize the safety benefit of this life-saving technology? What can be done to overcome FCC's ruling and save V2X? And are other countries around the world facing similar challenges? We will discuss these questions in our next episode when we talk with our guests from the Department of Transportation and ITS America.